were introduced to different ways to represent electrons last unit. For example, again, nitrogen, we would write 1s2, 2s2, 3p, 2p, 2p3. We could have done that with up and down arrows, which is called orbital notation. Different ways of representing electrons are important because electrons determine the main behavior of the atom. Recall the nucleus is really, really tiny, like the size of a marble inside of a football field, where the rings of the track are the outer rings of the atom. The electrons on the outside determine the behavior. They determine the bonding that things do. And this now beginning the bonding unit, we need to do more with representing how electrons play a role in bonding. You learned last unit a very important thing called the octet rule. This idea of 8 outer electrons leads to stability. What we have to do today is introduce another way to represent electrons. However, we are not worried about the inside electrons. The inner electrons are not our focus, pretty much from the year on out now. I mean, we have to remember our trends in the periodic table and how that, inner shells, electron shielding plays a role. But our goal today, with this first part, is to be able to map out the outer electrons. And the sheet you picked up on the way in that's titled Valence Electrons in Lewis dot Structures does just that. So first off, the top paragraph states the valence electrons are electrons in the highest energy level, the outermost. The s orbital holds 2, the p orbital 6, giving us our octet of 8. There are 2 exceptions to the stable octet. Hydrogen achieves a stable form with only 2 electrons because it fills the 1s. Kinsey, what's the other thing that's stable with 2 electrons? Helium. Actually, lithium ion could be as well, so there are a few others, but remember, noble gas configuration, full outer shell, those are stable. We are learning how to do Lewis dot structures because we can then show, again, how an atom looks like or how a molecule looks like. Even though technically it doesn't really look like that, just like up and down arrows isn't what an atom looks like. So the second part of this top section says how to do Lewis dot structures. And I'm going to skip the 2 steps and just look directly at that X at the bottom of or in the middle part of the page. You'll see an X there. And you'll see numbers 1 through 8 numbered around there. However, they're numbered kind of in a goofy sequence. If we asked you to do the Lewis dot structure for an element, you would first write down the element symbol. Let's say nitrogen, like the example I started with. And then you have to determine how many outer electrons there are. And in nitrogen, as you can see, I circled in green, there's 5 outer electrons. Now you can fill these electrons in a couple of different ways. If you look at that page, I say to put the first electron on the right, the second electron on the left, the third here, the fourth here, and the fifth there. I mean, if you wanted to do it that way, that's fine. Another way you could do it is write down the symbol N. I need to do 5 electrons. I'm just going to start at the top and go around in a circle. 1, 2, 3, 4, 5. That's perfectly fine. But one thing we can't do is do 1, 2, 3, 4, 5. The reason. Look back at the orbital notation. Notice how we have 1 pair of electrons and 3 lone electrons. Here's 1 pair, 3 lone. Here's 1 pair, 3 lone. Here is 2 pair and 1 lone. This example doesn't work. We teach you a certain way because drawing Lewis dot structures for atoms, it's kind of important, but not that important. Molecules and compounds is where we need to be able to draw these things for. And if we can teach you the correct way to do it for an atom, it helps you understand how a molecule or a compound will form instead. So if we're looking at the bottom of the sheet, there's a whole bunch of practice problems. It gives you like beryllium, again, nitrogen I just solved for, and it gives you sulfur. Some students would ask, well, how do I know how many outer electrons are there? Do I have to write down the orbital notation every time? No. Look at what column it is on the periodic table. Beryllium, for example, is in the second column of the periodic table. Everything in the second column of the periodic table has 2 outer electrons. So if I were to do the Lewis dot for beryllium, I'd put a dot on the top and a dot on the side. Again, I usually like to start at the 12 o'clock position. I just start working my way around. But don't pair them up right away. The nitrogen we already solved for. Nitrogen, look where it is. It is right after carbon. It is in that 5th column because we're going to ignore the D block. So nitrogen was 1, 2, 3, 4, 5. Which means, how many outer electrons would sulfur have? Somebody. Which column is it in? 6. If I were to do sulfur right below oxygen, so again, it might say in your periodic table 16 above it, but remember those 10 in the middle we're going to ignore. If I was going to do sulfur, I would do 1, 2, 3, 4, 5, 6. Why don't you take a minute right now to fill in the rest of that page? So again, we have all the answers to the front side now up on the board. If we flip to the back side, this is where we have to introduce how to do this for compounds. So a metal and a nonmetal coming together, if you recall from last unit, is called an ionic bond. What we are going to work on today with Lewis dot is how to draw out the Lewis dot for ionic compounds. Lewis dot activities are going to continue over the next couple of weeks. When we introduce a new type of bonding, we will go over how to draw out that molecule. So, I try to break this down into steps. Step number 1 says draw out the structure for the atoms listed below. To draw out for sodium, you should first write down Na. That represents, hey, it's a sodium nucleus and all its inner electrons. Randy, how many electrons should I draw around sodium then? 1. And then chlorine. How many outer electrons should be around chlorine, Paige? The nonmetal on the right-hand side of the periodic table. 7. 1, 2, 3, 4, 5, 6, 7. So know what you're starting with is basically what I'm saying for step number 1. Step number 2. An ionic compound is formed when the metal gives an electron or electrons to a nonmetal. Hopefully we remember this from last unit. That chlorine has a high electronegativity. It's good at pulling or taking electrons. Sodium has a low ionization energy. It's easy for it to lose. Sodium is going to give this electron to chlorine. Notice how there was one empty spot there next to chlorine? That's where that electron fills in. So this is the visual we want you to see of metal donating to nonmetal. Now step 3, what is our final answer? It says redraw your compound showing a full shell for the anion with an appropriate charge. The cation has no dots, but it has a charge. If sodium were to lose 1 electron, Noah, what would be the charge of sodium when it lost 1 electron? It would have now 10 total electrons, so it would be like neon. But when you lose 1 negative electron, what charge do you get? Look at the top of the column on your periodic table. What charge does sodium obtain? +1. When sodium loses a negative electron, it has a positive 1 charge. Similarly, coal, when chlorine gains a negative electron, it has a negative 1 charge. Again, it's on the top of your column. Remember when we went over these charges with naming? And we do include the 8 electrons around the chloride ion. So this would be the Lewis dot structure for sodium chloride. What we are going to do today is, I'm going to give you about 5 minutes right now to do a couple of the problems on this sheet below. Then we're going to work at the lab benches on this for a little bit. So we'll work with each other in groups to kind of show this visualization of how these ionic compounds come about. And then with the last little bit of class, we're going to remind you about a little bit from that reading guide of what a metallic bond is. So go ahead right now